Hi everybody, my name is Chris Armiger, and this is going to be my week 2 discussion on natural hazards. I was given the topic of tectonic hazards, so as we go through this, I'll be explaining to you essentially earthquakes, volcanoes, and then some of the natural incidents that can happen and some of the natural hazards associated with those, um, primarily and secondarily, and then some of the ways that we are looking to mitigate these sort of things in the future. And then we'll talk a little bit about the overall cost, and then end with kind of like a case study of, not necessarily a case study, but just more of an introduction into a natural hazard that's likely to develop into a natural incident um, in the expected future that we'll be dealing with in our lifetime. Okay, so let's talk about a couple things before we get into the specific hazards I had. We're going to just clear up a couple definitions real quick to make sure that we're kind of talking about the same thing and we understand kind of where some of the ideas we're going to talk about come from, some of the strategies we're going to talk about come from. So the first thing is, what is a natural hazard? So a natural hazard, if you've had classes like through the BS program and through the MS program, probably with Dr. Reynolds, then you've definitely had some sort of natural disaster courses. So what distinguishes natural hazards from natural disasters? Natural hazards are specifically distinctive because they would occur without interaction from humans. Without our doing anything to produce it or to encourage it. And these things would happen regardless. And then again, also the distinction is it's not really a disaster until it has some association with human life and the human environment in terms of human the cost of human life, financial impact, socioeconomical impact, things like that. So a natural hazard is something that's going to happen anyway. Hurricanes, storms, earthquakes, floods, those things are just part of nature, and until they interact with humans, they stay part of nature. They're just hazards to our environment. Once they impact or reach our environment, then they become an incident. So that's the distinction there. So this chapter was specifically about the hazards that we're going to face and we're going to try to mitigate and deal with as emergency managers, emergency planners, and so on. So then the next thing is kind of hazards identification. So when we identify a hazard, then we kind of identify it from sort of different approaches, different tiers. So there's primary. We identify a primary hazard. So it's like a big one. So because these are natural hazards, they're going to be kind of like earthquakes, volcanoes, droughts, blizzards, floods, and anything else that tornadoes, hurricanes, all those sort of things. So that's like the precipitating or primary event. And then when we get to the secondary level of identification, so now we're starting to look at, okay, what sort of other things kind of come along with that. So what's the next step, or what is that event? What is that hazard? What are the byproducts of it? What does it generate? So hurricanes are an easy one. A lot of people are familiar with them, especially in Florida. So hurricanes would be the primary event. What do they bring? They're wind storms with thunder and lightning. That's really what a hurricane is. So it's a tremendous wind and thunderstorm, rainstorm. But then as a result of that, you have flooding, you have storm surge, and then you have everything that comes after that, which is going to be the next level of tertiary hazards. So what are those? What are those secondary events trigger? They trigger people's homes being destroyed, communities being displaced, infrastructure being destroyed, changes in geography and topography, all those sorts of things. So it's saying it's a three-layered approach or three-tiered approach is sort of misleading. It's more like three different perspectives. And then finally is like the hazard profiling. So when we identify these hazards at whatever level, primary, secondary, tertiary, it doesn't matter. What we do is we kind of go back and look at historical references. Hey, what were the byproducts of this event, this hurricane in Florida back in 1906? Was it repeated in 1910? Was it repeated again in 1940 and 50 and 60 and so on? And then you can make predictions based on historical references, and then you can use those historical references to start calculating predictions, engineering predictions for the future. So when you profile an incident, that kind of is how you can start a lot of your mitigation, your resiliency. It's all part of planning. It's really part of the risk assessment. So we'll if we kind of understand those, then as we go through the presentation, we'll be able to kind of understand a little bit better maybe when we start talking about mitigation and the cost and what we're doing and where we're going. If we understand these things, then we can kind of stay on the same page together. Okay, so we're going to talk about my specific hazard, which is tectonic hazards. Tectonic hazards are pretty much anything that's associated with the movement of the big continental, what we know as the continental plates from school, or tectonic plates. There's 7 massive plates that make up pretty much the crust of the Earth. And then anytime you have any sort of anything that would come from that, any sort of event or hazard that's triggered because of movement or manipulation of those plates, it's a tectonic hazard. The 2 big ones, the primary hazards, are earthquakes and volcanoes. Those are most associated with these crustal plates or continental plates interacting with one another, and just their natural movement and progression. So you can see in the diagram next to it, you have this massive continental crust, and then the big ones that we talk about with this is this lithosphere, which makes up the crust, and then this asthenosphere. It's a hard word for me to say. That's kind of where the crusts float on top. So that second layer is you've got all this molten magma and gases trapped in the continental plates. The crust kind of floats on top of that. So that's where it gets its pliability to move. That's why they're not stationary objects. The Earth is not solid from its surface to its core. There's layers of molten material that's what allows the crust to kind of manipulate. And then we'll talk about the secondary hazards, the things that come from these earthquakes and volcanoes, which are primarily going to be tsunamis. That's the big one, especially with earthquakes. And then landslides, rock slides, and avalanches. Those are certainly associated with earthquakes and also with volcanoes. And then the last one, we'll touch on these poisonous gases. Those are primarily symptoms from from volcanoes. What's unique is that earthquakes are sort of a secondary hazard to volcanoes, but volcanoes are not a secondary hazard to earthquakes. So we'll start moving along here, and then we'll see kind of how they all intermingle and what we're going to have to deal with when these hazards become incidents. Okay, so let's just talk about these tectonic plates real quick. So there's really 3 different kind of ways these plates move. So you have, like I said, 7 massive plates, and you can see in the map to the right kind of where they all are. If you look at it, the outline of the plates closely resemble the shape of the continents and the oceans. Because as these plates shift, land masses move around, on top of them. They tear apart, or they get pushed together, and over, hundreds of millions of years, it's these tectonic plates are really what has shaped the natural landscape that we see and we experience, for both the land masses and the oceans. So you have these plates that are called divergent plates, and the divergent plates, they generate new crust, and they kind of move. They're always pulling away. They're under tension. So if you kind of look on the map, anywhere you see those divergent outlines, or where you're going to find trenches in the ocean, and you're going to find big trenches and cuts in land mass, where continents have separated. And if you were to take the Earth's continents and try to work it like a puzzle, you can kind of get them pretty close to being together. But these divergent plates, they pull. They're under tension all the time. And like I said, they have over the centuries developed what we recognize on maps as massive cuts in land surfaces, and these oceanic trenches. So the divergent plates, they pull material apart and open voids for material to fall in. Then you have these convergent plates. The convergent plates, they're obviously different. So they recycle the crust. Anytime you're talking about tectonics and you hear the word recycle, recycle also means like generate or grow or build. It's sort of a synonym for all of those things. When you hear recycle, try to think that like as the plates come together, they converge, they're forced together. They're pushing mass of material up, either because of their sheer weight or the pressure that they generate. So convergent plates, if you look at the maps, you'll recognize those blue lines. Most of the places where you see the blue lines are where you'll find some of the most mountainous regions in the world. So especially like if you look at the U.S. And you look over there all the way at the west, you've got the mountains out there in California and Washington and Oregon. And then when you go down Central America and down through South America, you've got all those mountains there, all the way from down in Mexico, Peru, Colombia, all the way down there, all the way through Argentina, the whole way down the continent. And those are most of the mountain ranges that people are familiar with, either from traveling or just through pictures and lessons in geography. But those are the result of convergent plates. They build those mountain ranges. And then the last one are these transform plates. They have different names: transform plates, transformative plates. The distinction with those is those neither pull apart or are forced together. They move horizontally. So they're kind of passing and cutting. That's where, like, if you were to take the map, right, and you were trying to put it back together like a puzzle, and just one piece didn't seem to fit or something seemed kind of out of whack, those transform plates, or if you can imagine, they're the ones that kind of twist the puzzle pieces around, because they're moving horizontally, they're not pushing or pulling. So they would kind of almost create spin. And when we talk about spin, I mean, you're talking about the most minute portions of a degree over millions and millions of years. But like I said, if you're trying to put the continents back together, anything that wouldn't quite jive or wouldn't quite line up is only because these transform plates are pushing and kind of twisting things along. So now let's talk about some of the faults that these plates generate as they move. All right, so like I said, as the plates move around, they generate faults, and there's a couple different kinds of faults. You have these, if you look at the picture to the left there, these strike slip, and that's where things go horizontally. So as as they move around, it's going to be those transform plates. They're kind of sliding masses in opposite directions, but not vertically. And then you have the normal fault lines, and they're have to do with the tension, the pushing and pulling. And so when something pulls apart, and the plates, so if you were to go back and look at that map or more detailed maps, they'll show you which directions the plates are moving. So just remember, if a plate, you were to take a single plate and say, look at it northeast, south, and west, if it's being pushed from the west, then it's pulling to the east. So at any rate, the normal faults, you kind of get that slip where as the plate is pulled away from the other, it creates a void, and then the natural mass will fall down into that void. And then just the opposite is thrust, the same thing. So if you've got separation on one side of the plate, then on the other side of the plate, you're going to have compression, and then that's going to lift. So that's just how it generates, different disturbances in land mass and shape. And those are subtle because these plates are constantly under pressure. They're under pressure all the time. They're moving all the time. It's so minute that most of the time we never feel it, but they're always moving to some degree. We only feel it when there's sort of like catastrophic releases and stuff like that in pressure. So we're going to talk about that in just a second. All right, so to the heart of it all is earthquakes. So that's our primary tectonic sort of hazard. So what is an earthquake? An earthquake is it's a seismic event that happens from like a sudden and aggressive and a violent release of pressure that's created by either friction, collision, subduction, or separation of the tectonic plates against one another. And the most devastating earthquakes, if you were to go through history and take a look at all these things, are the ones that happen in these convergent zones. So just to talk about, there's a word I want everyone to key in on when we talk about earthquakes, is this subduction. So subduction is kind of like, it's unique in that you have an area that you have a plate that when it hits another one, it's gonna try to dive under that plate. It can't push against it. It doesn't have enough strength, or the other one's too strong or too much pressure or whatever. So they don't bump into each other. One of them yields to the other, and it's going to dive under that plate. And then when it dives under that plate, it starts kind of moving underneath it, kind of at a bit of an angle, and then pressure, the weight of the other plate sits on top of it, drives it down, drives it down, drives it down. And then at some point, it's going to snap. And we'll talk about that in the case study at the end. But those tend to be the most dangerous and the most catastrophic. So like, these plates, they snag on top of each other. And, when the snag is released and the plate snaps apart, all that energy from that release of pressure, sends these seismic waves jolting through the whole Earth in various directions. And then depending on where you are in relationship to it is how much it's going to impact you. Also, like, the shallower an earthquake is, the more devastating it's going to be as well. So when we talk about these earthquakes and we're trying to research them, a couple of things we want to be aware of is like this focal depth. The focal depth is the distance below the surface that the earthquake happens, where whatever pushing, pulling, release of pressure, snapping, colliding, whatever happens. The focal depth is how far below the Earth's surface it happens. And then the focus is the specific point where it happens. And then this last little definition is the epicenter, and then that's the point on our surface where we feel it, where the focus is directed. So, say we have a plate that's 3 miles under the Earth's surface. That's our focal depth. The focus is the point where it's released. So it's going to be at that specific distance. And then the epicenter is going to be where the reverberation of those seismic waves come up and meet the surface. Because the focus and the epicenter are not ever specifically the same. Like you couldn't draw a line perfectly straight from one to the other, because the pressure and the reverberation of that wave, all the seismic waves, they can be deflected on the way up depending on where they happen in the crust, what's above it. So if you have natural vents because of aquifers or because of volcanoes, cave systems, whatever, it might change not necessarily the whole force, the whole concentration of the seismic waves, but they might be felt miles and miles away, because the waves meet less resistance through hollow space, obviously. So like if you have one in the ocean, the water is going to absorb a tremendous amount of it. If you have one that's under like a mountainous region, there's a lot more material there, and so on. So that's why typically the closer they are to the surface, the more damaging they are, because there's less material above that focus to absorb any energy. All right, so measuring earthquakes. Most people are probably familiar with the Richter scale. The Richter scale is it's a bit antiquated, but it certainly has its value. It's a mathematical calculation. It's an open-ended logarithmic scale. It relies on readings from seismographs to measure the intensity of the earthquake. So if it's less than 3, humans don't necessarily feel it. That doesn't impact our man-made environment very much. But then if it's greater than 6, that's kind of when we start feeling it. And then anything over 8 is pretty catastrophic. So then the next one is this modified Mercalli intensity scale. That one is kind of based on, it's a quantitative and qualitative scale based on observation. So this one's tremendously valuable, especially as we try to compare historic events to future events and make predictions. We kind of go through historical data and say, hey, look at this. This was measured at a 3 at this particular reading site. But 10 miles away, where we didn't have a seismograph, look at all of this damage. So then you use that to kind of figure out how, in specific parts of the geography, certain earthquakes, or rather how the earthquake impacted that region, and then you can score it that way. So you might have like something that measures a 3, say you have one that measures a 6, and it does X amount of damage in California, and then you have a 6 that does Y amount of damage in, North Carolina or something, or Tennessee. So if you just use that number, then it's hard to compare the scores from the Richter scale, because the damage will be significantly different, just because of soil composition and natural topography and those sort of things. Also, because of like population, like what's there. If it's out in Tennessee and there's one house for every 10 acres, and they're older homes, maybe they hold up well. It's all farmland. There's not a tremendous amount of damage. But if it's in California, where you have skyscraper after skyscraper, rows and rows and rows and rows and rows of townhomes and row homes and all that other stuff, and there's a tremendous amount of damage, it's not a good comparison based on the score. So the MMI allows you to score things based on observational data. And the last one with that Mercalli is, you'll see that bullet there down at the bottom is that there's no instrumentation involved in that. It specifically comes from surveys from people and places involved in that specific event. All right, so volcanoes is the second primary event from these tectonic sort of hazards. And volcanoes, so they generate kind of in this asthenosphere, which is that magma layer that the plates float on top of. So those plates are not, they're imperfect and they're not solid or absolute from one edge to the other. There's vents, there's cracks, there's fissures all throughout them. So when there's pressure or gas or molten lava is able to escape through any of those pockets, then you have what we recognize today as volcanoes. They're traditionally devastating events that are very hard to predict, just like the earthquakes, because the instrumentation just doesn't allow for very much warning. And the volcanoes will have the same sort of secondary stuff as the earthquakes associated with the hazards that will come after, which we talked about earlier in the presentation. So a couple different types of volcanoes. There's several. There's 2 pages worth of different types in the textbook. So just to save you some time, I went through all of them and did some research outside of the textbook about them. The ones that you're probably most familiar with from TV and just travel and pictures in National Geographic and stuff are these calderas. And they're the result of violent explosions. So if you look at the picture above the text on the bottom right, you'll see one of those calderas. And that's where it looks like the top of the mountain's been blown off. Like I said, they're the result of violent explosions where you'll have, there's a vent or a shaft where that magma starts to come up. And until it generates enough pressure, usually over hundreds of years, to blow the mass that's holding it down off, they just sit dormant until, like I said, until they build that pressure. But what's distinctive about them is when they blow their top, so to speak, they leave these massive craters. And then the next one that you'll probably recognize, and the ones that we'll deal with most in North America and even South America, in the Americas, are these composite volcanoes, because they're what we recognize to be mountain ranges. And the distinction between those and the calderas is they're made of, these mountain ranges are developed over centuries of just a steady lava flow. So they're not capped. Like the caldera at one point was capped, and then it blew its cap and left that massive crater. These composite volcanoes have a lot more fissures and vents than the ones that generate the calderas. So you just have more like a slow oozing of magma and atmosphere and pressure. And as it comes up through its vent shaft and then into these smaller branch lines, it cools and it just keeps adding land mass over centuries to build these mountain ranges without generating an explosion. If there are explosions, they're usually small in magnitude compared to these calderas. And like I said, you'll kind of recognize those anywhere you see a mountain range. Okay, so now we're to the point where we're going to talk about what are the products of earthquakes and volcanoes, and how do they really impact us? How do they hurt us as a civilization, as people, or just our lives in general? So what happens is when you have earthquakes and volcanoes, any sort of seismic event, right, that has to do with movement, vibration, whatever of these plates, then what happens is the soil that's below the surface and kind of between the crust, it essentially, they call it soil liquefaction. So what happens is the soil either is vibrated so it's compacted because of the weight of the surface of the Earth and sandwiched between the crust, right? So when we start making voids or separations, we either push the um, soil up or we create a void for it to fall down into, and then at the same time we add a tremendous amount of vibration to loosen that soil, or especially in volcanoes, it's magma. We think of the lava when we think of volcanoes, but there's also a tremendous amount of steam that's produced from those because of the heat and pressure. That the soil can become waterlogged, and then it just starts to slough into those voids, and then whatever's on the surface, it was built or constructed based on the density of the soil beneath it to stand. Well, once that soil has lost its density, then you have structural collapse. You have various infrastructure that's built into the soil will fail and collapse. Or the soil shifts and then dams break, dikes break, levees break, things like that, and then any sort of just like you have these topographical and geological shifts, and that's like when we went back before to those slides about the faults, where you'll have they'll slip, they'll move up, they'll move down, and then when the topography changes, whatever's inside of it's going to move with it. Whatever's above it's going to move with it. Whatever winds up being below it is obviously going to have to deal with it. So basically, that's how the earthquakes and the volcanoes hurt us. Is they just destroy the stability of the soil, and they alter the geography. So anything that we considered to be permanent or fixed that's attached to it suddenly becomes unfixed, and in most circumstances is destroyed. All right, so then the secondary hazards that are generated from those earthquakes on volcanoes we talked a little bit about before. The tsunamis, the landslides, poisonous gas. So we're just going to look a little bit closer to them. The tsunamis specifically is really the most catastrophic secondary hazard associated with the two primaries. And the tsunamis, if I'm sure everybody's familiar with them just from what they've seen on TV and stuff like that, is water becomes displaced. So you have this massive either shift in the contour of the geography. Mountains fall in or fall into the water. They displace the water, or the soil will erode, and then you'll have these massive fault lines. Either in the seabed or in the surrounding land close to the sea, where they'll fall in. And then, so either way, a tremendous volume of water is displaced, and it's displaced in a short time. So water is a liquid, obviously, and if you're a firefighter, especially if you're an engineer, you pump a truck, or you're an officer who used to pump a truck, or whatever, you have any sort of experience with hydraulics, then there's 6 principles of water that were beaten to your head when you took the state test, and hopefully they're still sticking around today. If not, you don't have any experience with it. Just think about it this way: is water is always trying to maintain its equilibrium, right? It's always to stay balanced. It can't be anything other than flat. It's going to fill whatever space it's in, right? And it's going to do it as quickly as it can. So when you have literally millions and millions of gallons of water, a tremendous metric space that moves rapidly like that, then that in itself will create a seismic disturbance, and then that will generate waves. And then when those waves get moving, there is a tremendous amount of force behind them, and they can travel for thousands and thousands of miles, literally across the Pacific Ocean. From one side to the other. And then what happens is, so when you're out at sea, there's a tsunami coming. You probably don't realize it because you have like this size. You have like it's like a ripple on a pond, right? So you have a small disturbance over a tremendously large, vast ocean. So it seems negligible because the energy is traveling at a tremendous depth in the ocean. But then as it begins to get shallow, the water is going to start to lift. And when it lifts, that's what generates the waves. And then as the waves crest and make landfall, then there's just, just total devastation. And these things can, travel at hundreds of miles an hour once they start developing momentum. So, if you know again, if you came from the fire department and you pumped a truck, a gallon of water weighs 8.35 pounds. And when you start multiplying that by billions, then it's just a tremendous mass of strength, going somewhere. And there's no amount of engineering. There's no building that's going to be strong enough that people can engineer to kind of withstand that. So you get a tremendous amount of devastation and some loss of life associated with it. And the tsunamis, unfortunately, detection systems are kind of getting better in the last 2 decades, but they're still not anywhere where they need to be, especially for vessels that are out at sea. And then you have the landslides, and we talked about that. That's the result of the liquefaction of the soil, and the landslides produce erosion. And with that, again, whatever structures are designed to be fixed become unfixed, and they're hazards. And the last one is the poisonous gas. We talked about it a little bit before earlier also, but that's specific to the volcanoes. So when that gas is released, in the asthenosphere, there's a tremendous amount of carbon dioxide. That's the main gas, and hydrogen, and there's some sulfur. And then when it mixes with our atmosphere, then you get the hydrogen sulfide and all these terribly toxic and poisonous gases that create an ideal H for humans and animals. So as they move with the wind currents, it's kind of like almost a nuclear blast. If I'm sure you've had that in a number of the classes. You have the plume, right? And then you have the fallout from the plume. The difference is that for the poisonous gases, it pretty much is going to affect the area that it affects, and it's not transferred outside of there. The issue that we have with the biological stuff, or rather the nuclear stuff, is you have the fallout, and you have the wave, and then you have people trying to flee the scene, and they're carrying radioactive isotopes with them. You don't really have that with this. So it's just kind of localized to the area. All right, so what are the impacts of these earthquakes and volcanoes, these tectonic hazards? So the human cost, I've read several studies about this in the text. So we have between this time period, you'll see the slide, between 1998 and 2017, so almost 20 years, there were 750,000 deaths across the world. A big chunk of that is going to be the hurricane in Haiti in 2010. There was over 200,000 people perished in Haiti. And then, more than 125 million people were affected during that period globally, and that is beyond deaths. So the 750,000 deaths, 125 million people affected. That means they were displaced. They had injuries. They were homeless, and that again is a lot with Haiti. Haiti had 200,000 deaths, and at least 8 million people were displaced. Volcanic activity, the something we didn't talk about that's really, it's not specific to volcanoes, but it's just infinitely more associated with volcanoes are wildfires. And in a 20-year period, 2,400 deaths, but it still affected 6.2 million people. And you've seen the wildfires in California. Those wildfires in California that were, had to do with land management are not associated to this number. This is specific to volcanic activity. I got a lot of these from a study from Harvard, so you can see in my references, you'll notice a Harvard study. That's where this all came from. And the financial cost over the last 120 years, 115 years was $10 trillion was the number they came up with. That's in the same Harvard study for just losses of they associated like GDP, what a person could earn in these hundreds of thousands of deaths over the last century related to hurricanes, or rather related to volcanoes and earthquakes. And it just shows you that even in a single year, there's about $6 billion in loss just in building stock losses. So that's, home inventory, commercial structure inventory, just buildings, infrastructure. So you can imagine how that impacts your the cost of insurance. You know what I mean? All right, so to talk about some mitigation a little bit, so what are we doing about it? Earthquakes, these seismic hazards are pretty tricky. So really the only way we can get ourselves out of trouble with these things, there's structural efforts and then there's non-structural efforts. There was a big conference in Delhi that had to do with this whole East Asian emergency management conference, and they talked a lot about earthquakes, specifically seismic activity specifically. So the biggest thing structurally is just to design buildings better, build it back better. That's our whole resiliency motto. But the issue with that is like there's just a tremendous amount of cost associated with that, and not so much in the U.S. or North America and even South America. It's not that big of a deal financially, but once you start expanding into the globe, India, Caribbean islands, Pacific islands, countries like Haiti, any of those third world countries and even second world countries, the cost to rebuild with resiliency, it's just not an attainable goal. There was a tremendous amount of life lost, and that building stock number is super exaggerated. It's not. I mean, it's accurate, but it's just exaggerated in the context that a lot of that loss comes from masonry building construction, brick and block construction. So the way you engineer it out, the hazard or the risk down, is to use more elastic material. If you don't know a lot about building construction, steel is much more elastic than concrete. So you want to incorporate steel in your buildings as much as you can when you're dealing with tectonic risk. And the non-structural just really has to do with codes that would enforce or encourage people to use those engineering principles to kind of mitigate against it. And then the last thing is this case study I had mentioned before. So this is something that we'll probably experience or deal with in our lifetime. Hopefully not experience personally, but we're definitely going to hear about it. So we've covered this in other courses, previously. But this is a really good one to look at because it's relevant in the space of time that we live in. So this, if you don't know about it, I'll give you just a quick walkthrough. This Cascadia subduction zone. So we were talking about that before with the earthquakes, how it's the most devastating and just worst kind of area to have a earthquake in. I live in Florida. I can't stop saying hurricane. So either way, it's the worst earthquake risk. So this Cascadia subduction zone, it kind of runs from Canada. Really, in the U.S., it's going to be Washington, Oregon, and then the northern part of California. So we talked before about those convergent and divergent zones. So you have like this big area here that creates a subduction zone because you have the landmass, that Pacific plate is kind of pushing up against the North American plate. And the Pacific plate is the weaker of the two. So what's happened is it takes a dive and it goes under that North American plate. And then so if you look at this illustration here, when it goes under that North American plate, what happens is that Pacific plate, as it pushes against the other, and it dives underneath there, that plate gets heated up. The crust that makes that plate gets heated up as it enters like that asthenosphere and the magma, and it starts turning into magma itself. So it weakens and it starts building even more pressure. And then the American plate, as it's resting on top of that Pacific plate, it's it's pushing down with its mass, because that tectonic plate, that's the Pacific plate, is, for intensive purposes, is solid, but that Pacific plate is sitting on top of magma. So that North American plate can press down on it, and kind of if you were to take a stick and snap it, that's eventually what's going to happen. And when that Pacific plate snaps, that edge that's underneath the North American plate snaps, what's going to happen is the Pacific side, where it snaps, right, it's going to go up. You can kind of see those arrows, it's pointing west. It's going to shove and send a tremendous amount of seismic force west across the Pacific, which is likely to send a just devastating and catastrophic tsunami to who knows where, Russia, Asia, all the way down to Japan, maybe even the U.S. Pacific Islands. There's just no way to tell. But then that other part that's facing east, that's facing the U.S., is also going to snap up and displace a tremendous amount of water, and it's going to push it towards the U.S. So the U.S. is also going to have to likely deal with a tsunami, as well as whatever land winds up being displaced along those the mountain range that runs up the coast from California up into Canada. And it's going to lift initially when it snaps, and then it's going to drop. And all that stuff's going to start crumbling away and falling off. And we're likely to see that in our lifetime. So that's just something to watch. And then the last thing I have is just this list of references. There's some stuff that's worth looking up if you have any interest in it. Like I said, that Harvard study is a big one. And then I also got a lot of information from World Health Organization as far as just how it impacts the country overall. So I look forward to your questions. I know this is kind of long. I intended to do a video, and after 3 days of research and calling Microsoft and just losing my mind on the phone with a bunch of different people, why I couldn't get a video button like to pop up on PowerPoint, I've come to find out, if you have an Apple, which I do, I have a MacBook, that is not offered on Apple software yet. So I'm going to have to find a different way to do a video for the next discussion. So I appreciate your patience. I know this was super long, but it was the only way I could get all the information in here. Thanks a lot.